Hello, and welcome to this video about permutations. Permutations are the building blocks of mathematical groups and are very useful in mathematics. They are used for finding all of the different arrangements of cards and lotto and bingo draws. I'd like to show you an invertible function that can map any natural number onto a unique permutation that can potentially be infinite. This natural number set will include the number 0, n0. Here is an example. I take the number 7 and map it onto this permutation. I hope that you are comfortable with this list notation to represent permutations. So this is what the function applied to 0 would be, the permutation containing only the number 1. It can be appended to a sequence of numbers in order of any length, and so can theoretically be infinite. It is the identity permutation where no numbers are swapped. This is the next permutation where 1 and 2 are swapped. And like the previous permutation, the rest of the numbers can be appended onto the end, so it represents the permutation for any length of numbers, where only the first two numbers or elements are swapped. The next permutation corresponding to the number 2 would be the swapping of these three numbers. Notice that now the number 3 is brought to the front and is involved in the swap, and like the previous two permutations, all of the other numbers in order would be appended onto the end, so that this permutation can represent permutations of any length, so that only the first three numbers are swapped. And this is the next permutation P3, and it can be the permutation of any length, so that only the first three elements are swapped around like this. This is P6. This permutation involves the swapping of four numbers. It is the first permutation of four numbers, because it is the factorial of 3, which is 4 minus 1. And this is P24, which is the first permutation which includes 5 in its swapping sequence, because 24 is a factorial, and like the other permutations, the rest of the numbers may be appended onto the end in numerical order, so that it can represent the permutation of any length greater than 5 that swaps these 5 elements. So now to construct a function that maps a number n onto a unique permutation sigma, we have to calculate where to put the number 2. We'll use the percentage symbol, which represents the modulo or remainder operator, which is used in C and JavaScript. So this is what x is. For the moment, this operation is simple. It is only n modulo 2. If n is even so that x is 0, we'll change x to be 2, which is the number we're modulating it by, and insert it into the second location of the list. If n is odd and so x is 1, we'll insert it into the first position and push the 1 down the list to occupy the second position. And now step 2, we'll have to insert 3 into the list. If n is less than 3, we'll finish here. If not, we'll have to find a position to insert 3, which is x. We'll calculate x according to this formula. And then we'll divide it by this number 2. We'll modulate it by the factorial of 3, and then divide it by the factorial of 2. And this number probably won't be an integer, so we'll apply the floor function to it, and get the next lowest integer. We can pack all of this up into this one equation. We can generalize this equation a bit more by including these factorial functions, which will enable us to get a much more accurate function for inserting the number I, which can be any integer. So now to insert the number 3 into the list. And if, for example, x was found to be equal to 2, we'd insert it into the second position and push 1 into the third position from the second position. And now for step 3. If n is greater than or equal to the factorial of 3, then finish. Otherwise, calculate x by modulating it with 4 factorial. then dividing it by 3 factorial. I'll just rewrite all of this at the top of the screen here. Then get the next lowest integer using the floor function. And we can pack this all up into this formula. So then if x was 1, then we'd insert the 4 into the first position and shift everything else 1 place to the right. So now to do step 4, we'll insert the number 5 into the list. If n is large enough, then we'll finish and not insert the 5. Otherwise, we'll calculate the position to insert 5, called x, using this formula. Then if x is 3, then we'll insert 5 into the third position, like this. In step 5, we'll insert 6 into the permutation list. If n is large enough, then we'll finish. Otherwise, we'll calculate the position for this number using this formula and naming its variable x. We'll expand out the factorials in this line here. And if x is calculated to be 4, we'll insert the 6 into the fourth position here. We can generalize the ith step. We'll finish on this condition here. Otherwise, we'll calculate the position of this number using this formula. And this is the computer code that we'll use to construct this permutation from this number. We'll use the splice function to insert this number into the array at position x. Although the formula for x looks very complicated, the rest of the code looks quite simple. So now to look at some concrete examples of how to calculate a unique permutation from a natural number. We'll show that this equation is true. We'll start off with the identity permutation. We'll calculate the position to insert the number 2. So it goes into the first position like this. Then we'll insert 3 into the list. This will be the formula to calculate where to insert it. So x will be 0, and there's no 0th position in the permutation. But if x is 0, then we'll set x to be equal to 3. So we'll insert it into the third position like this. Now to insert 4 into the list. This is the formula to calculate its position, which we'll store in the variable x. And x will be calculated to be 1. And so we'll insert 4 into the first position. Now to insert the number 5 into the list. We'll calculate where to insert it using this formula. And x will be calculated to be equal to 1. So we'll insert it into position 1. And so this completes the calculation of this permutation for the number 31. And now for another concrete example. We'll calculate the permutation corresponding to the number 79. We'll start with the identity permutation. We'll calculate where to insert the number 2 into it. Then we'll insert it into this position and push everything to the right of it, 1 position to the right. We'll then calculate where to insert the number 3 using this formula. And so we'll get 0 as the value for x. Whenever x equates to 0, we'll equate it to the number being inserted, which is 3. We'll then insert it into this position. Now to insert the number 4 into the position given by x. And x is equal to 1. So we'll insert it into the first position in the list. Now to insert the number 5, we'll calculate the position to insert it using this equation. And so x is equal to 3. So then we'll insert it into the third position. So this is the permutation number 79. Now to create the inverse function to get back the number that we started with from the given permutation. We'll get the largest number in the permutation, which is equal to the amount of numbers in the list, and then set the variable I equal to this number, which in this case is 5. Total is the variable we'll calculate by adding lots of numbers to it during a loop, so we'll reset it to be 0 initially. Then we'll get the location of the largest number, which in this case is 1, because 5 occupies the first position. If it was in the last location, we'll set this variable equal to 0 instead of I. We'll then increment the total by this amount. So this is what the total is so far. Then we'll remove this number from the list, and we'll get a new list with a new length and largest number. We'll get the new largest number in this list by subtracting 1 from the previous value. So now we'll repeat all of these steps with this new list. We'll get the position of the new largest number and store it in X. And if it was in the last location, we'll set X to be 0 instead of I, which is 4 in this case. Then we'll increment the total by this amount, so this is what the total is so far. We'll remove the largest element from this list, and then we'll get the new largest element of this list. Now we'll continue these steps on this new list. This is the location of the new largest variable, and it just so happens that its location in the list is equal to the number itself, so we'll set X to be 0. We'll increment the total like we've done before. Then we'll remove the largest number from this list. We'll then decrement I to become the largest number in this new list. We'll repeat these steps for this new list. We'll get the location of 2 in it, which is 1, and X will remain equal to 1. And we'll increment the total like this. We'll remove this number from the list to give us this list, which is the identity permutation. We'll get the new largest number in this list, which is 1. Then we can exit the loop, because I will be equal to 1. I'll just rewrite this last step. The number corresponding to this permutation will be equal to total, and in this case is 31, so this function can return the number used to create this permutation by the first function. So this is an invertible function. I'll just write out this result more formally. This is the computer code used to perform this function. I've used standard JavaScript code to find the index of the element in this list, and then to remove it, so the code looks a lot more simple. This is the code that I used in JavaScript for the forward function that creates a permutation from a number. I've used the array called permarray to store the permutation as a list of numbers. The first entry is used to store the length of the list, and is also equal to the largest element. I've set this particular location at the end of this function. I've also used a variable called kk to stop this while loop from being an infinite loop during the construction of this function. I've decided to store the factorials in a special array to save time, and fill it using a special function. This is the inverse function. I've set the first element of this array to be -1, so that these index of and splice functions will work correctly. And here is the testing function. I did use 8 of them during the construction process. This one tests both of these functions for numbers up to 10,000 to see if it works by constructing a permutation from a number, then getting this number back from this permutation. It doesn't work as well for very large numbers because they aren't stored precisely enough. So this is a sort of proof that it works, although I don't know how to prove it properly yet. So I hope that you have enjoyed this video and have learnt something from it. Please click like and subscribe if you did. Feel free to write anything helpful in the comments, and to share this video any way you like. And thanks a lot for watching.